morning, everyone. Or good afternoon, rather. Good afternoon. How are you?
Good.
Awesome. All right, let's go ahead and get rocking and rolling here today, because we do have a short class. We are shorter than all the other class periods. Looking into our notebook. Shh, ladies. Thank you. Looking into our notebook, the last lecture that we really did was this one, Classifying Triangles, was done for you on YouTube before we went on break. Hopefully you all have had a chance to go and take a look at that video, write down the notes. If you haven't, the notebook will be available for you after class. You can take a picture of it and copy it in. You will need a page for KWL for the assignment that goes with that one, still being graded. And the very next page will be the start of today's lecture. Today's lecture topic, if you notice, does not have a lesson code. This is because as I was going through the textbook and trying to find a good lesson that had this, I wasn't really happy finding it. So this one is not going to have a lesson code. What we're going to be working on today is we're going to be working on identifying the different types of geometry. I hope that you guys are going, wait, what? There's different types? There's different types? What? Yeah, there's different types, and we're going to be able to tell them apart. And the way we're going to tell them apart is by identifying and counting the number of parallel lines that we find in this geometry. And I hope that right now some of you are going, wait, what? It's really warm in here.
Yeah. Can you want to open the door?
Yeah, come on.
Or that one?
Not that one, that's too cold.
What?
All right, are you ready for story time? Okay, so for the next part of this lecture, it's just story time. You don't have to write anything. Yay! So you guys just to kick back and watch my little movie. I have a little movie that I will be doing in front of you. It's like puppet theater, only geometry style with stick figures. Anyway, once upon a time, ages ago, okay, not terribly long ago. All right, like 3,000 years ago. When we would draw stuff, it would be either on the floor or, you know, a sheet of paper or something. And all we had was our little pencil and maybe a straight edge and a compass. That's supposed to be a compass. I know it doesn't look like one, but it's supposed to be one, so pretend. And we'd use it to draw circles and straight lines. And this is how we started to represent the world around us. And it was all super awesome. Along came this guy, Euclid. There he is. There's his portrait. There's his. He's not Chinese. He's Greek. Yeah, he's from ancient Greece. You learned Euclid. Awesome. What did they tell you about Euclid? We're not really sure, but we heard of his name.
Isn't he like the father of geometry?
Yeah. Yeah, he's the father of geometry because he spent a lot of time thinking about geometry and shapes and stuff. And he's the father of geometry because not only did he just think about this stuff, he certainly didn't make them up. I mean, he gave us a lot of definitions and things, but he used these definitions and he wrote them down into a series of books. The first of which we have the newest edition of. It's right over there. It says Geometry. He basically wrote the first edition of our textbooks. The information really hasn't changed. It's just in a slightly different order and more colorful pictures than what they had back in the day. But the father of geometry, he spent a lot of time thinking about, you know, shapes and things. And one of the biggest things that he thought about was, you know what? I want to have a way to describe and explain all of the natural world in such a way that the Greek gods themselves couldn't come down and argue it with me. Well, I mean, they could try, but, they'd lose. That would make him a very happy person. And so he came up with the definitions for points and for lines and for planes, and he used those to build definitions for triangles and quadrilaterals and all these great things, right? Well, one of the things that he said was a postulate, that thing that you just have to take for granted and don't question him on, was something that said this. If you have a line, and you have some point that's not on the line, how many lines can you draw through that point that will never touch the first line that you drew?
Parallel.
That's parallel.
Wait, what?
How many lines parallel to this first line can you draw through that point?
One. No, none.
None.
Whoa.
What?
Only one.
Only one.
Yeah.
Only one, because look, he drew it. It's right there. Okay, my line isn't straight, but just pretend it is. Right? There it is. And that's what he said. And for a long time, everyone was like, awesome, Euclid. We love this. You were amazing. There's one line that's parallel to this other one. We're super happy. And then some people started thinking, wait, you want this system, this mathematical, logical thinking system, that you could argue against the gods of how reality is supposed to be done, and you're telling me that I have to accept this without you showing me why? And he was like, well, if you need to know why, look, there it is, I drew it. And they're like, Euclid, bro, come on, man. Yeah, get your act together. All the other things that you said, no, you can't just draw it. You have to have, proof behind it. He didn't have for this. All he said was, look, I drew it. And everyone was like, eh. And so people started thinking about this and started wondering, is this really a postulate? Or is this something that can be proven? And so they went about trying to prove this thing, to show that this was always the case. Enter this dude. He just disappeared off the thing, I'm sorry. His name is Riemann. I have no idea where he's from. He might be German, I don't know. Yeah, Riemann. He's got an awesome beard and pants. So here's this dude Riemann with his awesome beard and his awesome pants, and he's sitting here thinking about this idea of, well, how many parallel lines do we have that go through a point? And he goes, well, Euclid was drawing on flat stone and flat pieces of paper, and that's pretty awesome, but Mr. Euclid, not that he could talk to Euclid because Euclid was way dead by this time, but Mr. Euclid, what if we drew on this thing? What if we drew on the surface of a ball? We need to have a straight line on the surface of this ball. You guys played with this on Thursday and on Friday before we left. How did you get straight lines on this thing? Use paper, yeah. Yeah, you grabbed a paper that was a straight edge, because this straight edge you can fold and bend and do all sorts of crazy stuff. And so you totally just smacked, whoops. Technical difficulties, hang on, sorry. You totally just laid this piece of paper down on the surface of the sphere, and you traced it, and ta-da, there's your straight line, right? So do you agree with me that this edge right here is also a straight line?
Yes.
If we use that same technique? Yeah, okay. So these are straight lines in its entirety on the surface of the sphere. They're called great circles. All right, so we have these great circles. It's kind of like the equator. And so we pose the same question. Riemann sat and he asked the exact same question that they were asking about Euclid. How many lines could you draw through that point right there that would never touch this great circle down here? None? I don't know, let's try it. I have my bendy straight edge. All right, there it is. Push it straight, and no, it crashes down here. Can you see it where my finger hits the paper? It's crashing. So that one isn't it. What if I turn my paper? What if I did it this way? Surely that's not going to touch, right? Oh, but I have to smooth it out. Okay, so I'm smoothing it out, and crashes. So you're right. There isn't a way for me to draw a straight line, another great circle, on this sphere through this point, such that it's never going to crash with this other great circle. Which means that on the surface of this thing, there are no parallel lines. Let's think about this for a minute. Euclid said we had one parallel line. Riemann came around and said we had no parallel lines. Other people got to thinking about this. Y'all took Algebra 1, yeah?
Yes.
You remember systems of linear equations?
Not familiar?
It sounds familiar, where you had a bunch of lines like this and you were wondering how many solutions you had?
Oh, yeah.
Yeah, and you ended up with something like this. How many solutions did a system like this have? Just the one. The intersection. Where two lines intersect, that is a solution to the system of equations with those two lines. So in this one, there's one. What about in this setup? How many solutions does that have? She's shaking her head. This one doesn't have solutions. Those lines never intersect. They're parallel. So they're never going to have solutions. Did we have a setup? We had a setup for one. We had a setup for none. Did we have a setup with more than one?
No. Wait, yeah? Can you be like on top?
Yeah. If the lines are right on top of each other, put it away. It's distracting you. When we put the lines right on top of each other, we end up with unlimited, an infinite number. Yeah, exactly what y'all said. An infinite number of solutions to the system of equations. This is suspicious, don't you think? We have Euclid saying one, we have Riemann saying none. If this were a system of linear equations, there should also be an infinite number of lines parallel to one other line that all go through the same point. And what on earth would that thing look like?
Is there still people out there right now that trying to prove that stuff wrong?
That are still trying to work on it? Yeah. One of the main guys, though, that started this conversation of trying to find the infinite number was this guy, Lobachevsky. You'll see his portrait pop up in the little slideshow at the bottom in a bit. You'll recognize him by the very angry face. I think he's mad because he has no pants.
Is that him?
Yeah, him. See, he's angry.
He doesn't have any thighs.
He doesn't have anything. Like, he's got a medal and a turtleneck, and he's not happy about it. Okay, so this dude Lobachevsky, he was thinking about this whole idea of, well, we have a system where there's one parallel line. We have a system where there's none. Is there a system with infinitely many? And through a lot of hard work and hard thinking from him and from others, they devised this thing. Remember this guy?
Yes.
This is our floppy paper. I asked you guys to play with it before we left, didn't I?
Yes.
And you were asked to draw triangles on this. A lot of you were like, I can't draw a straight line on this thing. Yeah, it's not possible. Ah.
I think
And
it's possible.
anything's possible. Well, a lot of you did this. A lot of you did that. And you folded it. And the moment you fold it, it becomes flat. Becomes like Euclid's world. Not like Lobachevsky's world. We wanted to keep it like Lobachevsky's world. Here's a solution. It took a 6th grader to show me this. Yeah. You agree that this right here is straight, yeah? Okay, ready? I just drew a straight line on it, yes? Straight line. Totally doesn't look straight. Looks like it curves, but it's straight. All right. So there's a line, and there's a point, that's not on this line. And so I pose the question again, how many lines can I draw through that point that will never intersect that line?
What line did I conceive?
This line.
Oh, that one?
This one. Let me make the dot a little, let me make it here. All right, so how many lines can I draw through this point right here that will never intersect that line right there? One. The one that's parallel to that one. Okay, so that looks parallel. Kind of had to fold it a little bit. Sorry that it's bending and hiding a little bit. There we go. That line's straight. You agree with me?
Yes.
Awesome. Okay, so I didn't hit the point. I'm sorry. Well, it certainly doesn't look like they're going to touch, does it?
Nope.
They certainly look parallel, sort of. Because this one's... Yeah, we're going to pretend they're straight. Well, they are straight. Look.
Oh, yeah. Oh.
They're totally straight. And if I maneuver... Yeah, those are parallel. Look.
Yeah.
And I'm not folding or pinching the plane at all. I'm bending it a little bit, but it's already bent. Who cares, right? All right, so let's see if I can draw another one.
Okay.
Okay. Totally different line from the first one, yes? We're looking at this one now. Will it intersect that blue line?
Yes. I don't know. No. Oh, wait, which one?
This one right here.
Yes, it'll intersect going over here.
Where?
What's gonna intersect eventually, like, what Evan said?
These totally look parallel, though.
No, miss, it's not going in.
The other one.
This other one,
Yeah,
but
that
you
one.
said that one was parallel. Look.
Because you're folding it.
But I'm not folding it. I'm just maneuvering the plane a little bit to make it easier to see.
Oh, it does look parallel.
Those are parallel also. They're not going to touch.
So they're not gonna touch.
But so is these. So are these.
And with paper.
The way you
But I'm not
bend it.
folding the paper. See, there's no fold in there.
Not what you just bend it.
I'm just letting the paper flop and move the way it can. The moment I put a crease in it, a fold is when things break. But I'm not putting a fold in it. I'm not breaking it. I'm letting this paper move around so that I can see it. Can you see how there might be another line in here? And another and another? This is what Lobachevsky started on. This is what that plane might look like. And so these are our three flavors of geometry, where everything is flat and you only have one parallel line. Where everything is curved smoothly and round like a ball, where you have no parallel lines. And then Lobachevsky's world, where everything is weird and floppy like this one. And you end up with a whole bunch of parallel lines. Let's formally name these and write these down, and then sum it up and we'll be done. Okay? So here we go. Time to write some stuff. Our first flavor of geometry is called Euclidean Geometry. Brought to you by Euclid and ancient Greece, home of the Parthenon and Achilles. I don't know, I'm just making stuff up right now. If you can draw a picture of Euclid there and you want to, go for it. Here's my little portrait. Or you can just write his name. It's fine. And here's what his type of geometry says. If there is a line and a point not on that line, then there is only one line. How do I want to say this one? One line through the point that is parallel to the other line, the first line that you drew. That's what his parallel postulate said, and pretty much it's almost exactly how he wrote it, except he wrote it in ancient Greek and I wrote it in English. But this is what everyone, had everyone up in arms. Because unlike the rest of the things he gave us, the definition of point, thing that has no size and no shape, it's but a location. That was Euclid. Almost word for word. Definition for line, a thing that has no width but an infinite length, straight from Euclid. Plane, a thing that has no depth but it has length and width and goes on forever. Almost a direct translation from his definitions. He gave us all these very clean, concise things, and then he said this. And this is why everyone went, nah, prove it, buddy. Up next.
The math is like history.
Yeah, it really is. Up next was the world from Riemann. There's his portrait there on the right. And his geometry was called spherical geometry, is called spherical geometry. And it's called spherical geometry because it happens on a sphere. Look, mathematicians are not very creative when it comes to naming things. Don't be hating. And his geometry says this. If there is a line and a point not on the line, then there are no lines through the point that are parallel to the other line. And that's what Riemann worked on giving us. Then came Lobachevsky and a host of others who worked on the idea of what if there's an infinite number of parallel lines. And his geometry came to be called hyperbolic geometry. Now, please know Lobachevsky wasn't the only one working on this. He's just kind of one of the main figures that led us toward it. His geometry says this. If there is a line and a point not on the line, then there are infinitely many lines through the point which are all parallel to the other line, the starting line that we started with, and the hypothesis of this conditional statement. This is all well and good, but these three flavors of geometry have very real consequences to otherwise very familiar objects and shapes. I'd like you to take what's left of your note-taking space and divide it equally into 3 columns. Label one column Euclidean Geometry. The other column Spherical Geometry. And the final column Hyperbolic Geometry. So we know each of these geometries are characterized and differentiable, okay, that's a word, by the number of parallel lines that we find in them. But these numbers of parallel lines have something very important to tell us about the nature of triangles in the space. When we were doing the experiment Thursday and Friday, where you were drawing on flat paper and spheres and floppy paper, you were drawing on Euclidean planes, spherical planes, and hyperbolic planes. The flat sheets of paper were Euclidean geometry. Can you remember what kind of angle sums you were getting for these triangles? You were getting 200 for the flat triangles? How much? 180, yeah. And a lot of you recognized that you wanted those sums to be 180, and so you kept remeasuring and redrawing until you forced them to be 180. Okay? This is what you're used to. Triangle angle sums in Euclidean geometry on flat sheets of paper where you have one parallel line are 180. Period. Always. Now, as you were working on the surface of the spheres and you were adding up those triangle measures, what were you noticing? You got like 200 for sure on that one, on most of them, yeah? I think one group, was it this class or another class, ended up with a triangle angle sum of over 400. And it was a legitimate triangle. It wasn't this class, it was another class? Okay, I had a group that was 400, huh?
I did it wrong with study.
Okay, the triangles weren't big enough then. Yeah, and you were stuck wanting them to look like this. Yeah. And the problem is that your world changed, ladies, later. Your world changed. You were in a different universe and suddenly there were different rules. And in this universe, the rules state that triangles have an angle sum that is more than 180. The final one, hyperbolic geometry, the floppy paper triangles. What kind of angle sums were you getting there? Let's look at this example that one of my classes left me. Here we go, legitimate triangle on a hyperbolic plane. We have two angles here that are both 38. We'll call it 40 because it's easier to add. So 40 and 40 is 80, which means in order for this to be Euclidean, this would have to be 100, but this is less than 80. Which means that this angle sum for this triangle is way less than 180, isn't it? It's closer to like 150 or 160. And so in hyperbolic geometry on that floppy plane given to us by Lobachevsky, triangles add up to less than 180 degrees. Here's the good news for you guys. we will be spending the rest of the year working in Euclidean geometry. Our triangles will have sums that add up to 180 degrees, and everything that we work on, from defining what a square is to a rectangle to, hexagons and octagons and all of these other properties, the areas of all of these things are all going to be based on the fact that triangles add up to 180 degrees, period. But if you go into a career in which you are having to calculate distances and angles over large distances across the surface of this planet, you are working in spherical geometry. Because Earth is a sphere. Its surface curves this way. And so when you build a triangle out of 3 cities that are in 3 different countries in 3 different parts of the globe, your triangle angle measures are not going to be 180, they're going to be something bigger. And I have no way to tell you how big. I don't know.
So the Bermuda Triangle is really a triangle?
Oh, it totally is a triangle. It's got 3 sides, but it's not going to add up to 180 if you measure those angles. It's going to be something more. Because the Bermuda Triangle is big enough that this curviness, ladies, that this curviness of the surface of the Earth can be felt. If you go out to the football field right next to this building and you draw a triangle on there and you measure those angles, it'll likely be 180 degrees.
How big?
It's not big enough for the curve of the Earth to be felt. But if we drew chalk lines from here to, say, I don't know, Reynosa or Matamoros, and then up to, I don't know, Corpus Christi, and we measured those angles, that triangle's likely big enough for us to start to see this effect of the curve, which makes the angles more than 180. Now, hyperbolic geometry you probably are never going to run into, ever, in your life. But I want to put it there for you because right now there's some arguments going on in theoretical astrophysics. These are people who are looking into the very fabric of the universe, trying to do very much the same thing Euclid was doing 3,000 years ago. They're trying to figure out how to describe the nature of our universe. And right now there's a conversation, an argument going on saying that the universe is shaped like this. I don't know. And neither do they. But they're arguing that it can't be flat, like this, a flat sheet of paper going on for forever. And so there was an argument, well, if the Earth is flat to us, but at large scale it's curved like a sphere, it's a ball, well then maybe the universe is round and we're living on the inside of it, and we're looking at the inside surface of the giant ball, and people are going, that makes no sense. Maybe it's something weirder like this because, I don't know, light rays are doing weird I don't know. And I don't even think that they know really yet. But the neat thing that I want to give you now is put this in the back of your head. Because maybe you end up in a field and maybe you end up thinking about these questions and maybe, just maybe, this is the puzzle piece for you that is the key to the question. Maybe you have the answer from this little moment and this little conversation of, wow, this was weird. Okay?
She's all,
No inspiration.
It was. I tried. Thank you.